Oh, I think we were just gonna. There we go. Okay. All right.
Okay.
We'll start getting rolling here. Welcome everybody to session 8 of the ninth Microquasar conference. This afternoon we have Joseph Neilsen from Villanova University to tell us about winds in accretion disk systems. So Joey, again, I'll give you a 5-minute warning 20 minutes in, and I think you can start.
All right. Thanks, Mike. So yeah, thanks very much for the invitation. And I know it's been said already before, but I really do want to thank the conference organizers for organizing this and making the hybrid format work so well, as it's been really great so far. I'm sorry that I can't be there with all of you. My first real conference was the 7th Microquasar workshop in FOCHA, and it was wonderful, and this has been great so far. So again, real pleasure to be here. So I'm going to talk about accretion disk winds, and I've tried to organize this talk around some open questions and future prospects. But let me start by talking about winds. There's a big wide world of things of what we mean when we say winds in accreting systems. Stellar winds, there's magnetic winds, there's winds that confine relativistic jets, so there's ionized outflows from accretion disks. And just to be clear, very clear about what I'm going to talk about today, I'm going to focus on X-ray absorbing winds, and not entirely because I'm primarily an X-ray astronomer, but there are also a lot of good reasons why these outflows are good diagnostics of what's happening. And part of that is because at the same time as you're studying the outflow in X-rays, you can also be studying the behavior of the inner accretion flow in corona, as we know. So these winds, these hot outflows, have lots of X-ray observable properties, which I'll talk about in a little bit. And as Natalie mentioned in her Rennes talk on Tuesday, there are also winds in the optical and infrared that we need to be thinking about as well, and I'll allude to that towards the end of my time as well. So the general outline for my talk this morning and this afternoon for you all is I'll talk about a little bit about what we know about accretion disk winds, what I think we might know, what I think we don't know, and then a few things of what we can do about it to keep moving forward. So as far as what we know, I would put the things that we know about how accretion disks work under the category of details. And I'll kind of get to the parts about that we don't know later on. Again, there's a nice, Natalie gave a nice summary of some of these points on Tuesday. So the things that we know about winds from an observational perspective, we know that these are blue shifted outflows. So if you look at the X-ray absorption lines here, this is a plot from John Miller's paper in 2006. You see the observed absorption lines are found at shorter wavelengths, so higher energy from the rest wavelengths of these lines. Therefore, we know that they're blue shifted. They're moving towards us away from the black hole. We know that this gas is ionized, it's hot. Typically, we're thinking of gas temperatures in the 1,000,000 degree kind of range, maybe a little more, maybe a little bit less. And just to do a brief primer, when we look at these absorption lines, we're seeing a few things. When you look at the depth of the absorption lines, we can relate that through things like the curve of growth to the column density, or in particular, the ion column density, the amount of gas that there is along the line of sight. There are a few other factors that go into that, but that's one of the things that we're looking at when we look at the depth of those lines. When we look at the width of the lines, assuming that you can resolve it with your instrument, you're seeing dynamics, right? You're looking at things like turbulent velocities in the gas. You're looking at, you might be looking across multiple streamlines of gas, and therefore you're learning something about the sort of the launch dynamics of this outflow. And when you look at the ratios of different lines, specifically different lines from different ions or different atomic species, different elements, those ratios are what tell you about the ionization of the gas. So there's quite a lot of information just in the shapes and depths and ratios of these lines. Okay, so we know about their ionization. We know that the outflows are persistent. Now, what I mean when I say persistent is that they last longer than the time that it takes them to cross the system. So here's a 50 kilosecond observation of GRS 1915 from Ueda in 2009. And when you look at the beginning of the observation, you see this, this is the Chandra grading spectrum underneath. Nice strong absorption lines from the accretion disk wind. When you look at the second half of the observation, so, you know, whatever, 8 hours later, you also see an outflow. So what I mean by persistent is that you look, you come back a while later and it's still there. Talk about variability in just a second. The other thing that we know about them is that these are equatorial outflows, and this goes all the way back to studies of high inclination dipping X-ray binaries, where Maria Diaz-Rigo and collaborators noticed variations in the ionization and column density of gas when systems were in dip phases and not in dip phases, and that also comes out in work that on high inclination black holes that Gabriele Ponti did, that I'll be talking about in just a minute. So these are outflows that are basically confined, at least to some extent, to the equatorial plane of the binary. We also know that they're variable. This is a plot of the absorbed flux as a function of time during a limit cycle oscillation in GRS 1915. And if you look at the time scale, it's clear that we're seeing variability in disk winds on time scales as short as seconds, a few seconds in this particular system, which we all know is a bit on the pathological side. When we look at same system, but in longer timescale variability, looking at oscillations that last thousands of seconds or up to hours, we also see variability on those timescales. So we have variability in wind absorption on timescales of seconds and timescales of hours. And when we go all the way to the life cycle of black hole outbursts, when we look at the hardness intensity diagram, has been introduced a couple times so far in this week, where on the y-axis we have luminosity and a proxy for spectral hardness on the x-axis, and systems follow this counterclockwise Q-shaped pattern. Gabriele Ponti did the statistical study of detections of accretion disk winds, and those are shown by circles in this diagram. And you can see that they pretty well cluster up along this top branch of the hardness intensity diagram. So you see a lot of detections up here in these softer and intermediate states, and not a lot of detections down here in harder states, where we tend to see jets. So I would say that these are the things that we basically know about how accretion disks work around black holes. That's on the observational side. On the theoretical side, one of the things that we know is the mechanisms by which we think they can operate. The driving mechanisms, the launch mechanisms, include radiation pressure, Compton heating or thermal driving, and magnetohydrodynamic processes. So here are a couple snapshots from simulations. The one on the left here is a radiatively and thermally driven wind from a recent paper by Nick Higginbottom. And here on the right, we have a thermal wind and a magnetothermal wind in simulations from Waters and Proga in 2018. So we have a pretty good sense of the physics that produces outflows from black hole accretion disks, at least theoretically. Another thing that turns out to be important is not just can you produce an outflow, can you make gas flow away from the disk or away from the black hole, but can you observe it? And one of the quantities that turns out to be really important, one of the diagnostics that turned out to be really important for that, is the thermodynamic stability of the gas. Is the gas that you're looking at, or that you're trying to look at, in stable thermal equilibrium? And if it's not in a stable thermal equilibrium, then you're not going to be able to observe it as line features in your spectrum. And so we see these stability curves. This is from a paper by Pop that I'll talk a little bit more about later, where what you're looking for is periods where places where the slope of this line is negative in temperature versus ionization over temperature. Where that slope is negative, that gas that you might see there is thermodynamically unstable, and you won't observe it. So, so those are two of the most important considerations that we've focused on in the last 20 years or so, thinking about, can we observe these systems or not? So those things that we do know. As far as what we might know, I think that what we might know is the mass loss rate. And the reason that I say we might know the mass loss rate in these winds is because the mass loss rate depends on assumptions that you make about how the gas is ionized, about the density in the gas, and the geometry of the winds. So some of this is model dependent. A point in favor of the idea that we understand these mass loss rates is that when we do the calculations, we tend to get similar answers, which is that the mass loss rate in the wind appears to be comparable to the accretion rate at the event horizon. So if you assume a sort of quasi-spherical outflow and convert the luminosity into an accretion rate, you get numbers that are comparable to each other. In some cases, you get numbers where the mass loss rate in the wind appears to be much larger than the accretion rate at the event horizon. So we know that these outflows, in some cases, may be carrying away significant fractions of the infalling gas. And Natalie mentioned a couple other examples of that in her talk as well. And why is that important? Well, if disk winds are carrying away a significant fraction of the mass supply to the outer disk, it's fair to say that they're playing a significant role in governing the accretion rate at the event horizon. Now, whether the actual dominant effect is the controlling the mass accretion rate or governing the evolution of outbursts in different ways, Guillaume and Bailey have brought our attention several other ways that this can happen via scattering and irradiation from thermal winds or torques from MHD winds. I think the upshot is that whatever the exact mechanism is, these outflows are really behind the scenes shaping the outbursts that we see from accreting black holes. So I think they're worthy of detailed consideration. So this is a picture that I think illustrates the state of what we know. But I'd like to turn to what we don't know. And if I can put an umbrella to it, I think that at this point, we still really don't understand the origin of accretion disk winds. We have a lot of details. We have a lot of the puzzle pieces that we have collected, but from an observational perspective, I don't think we understand that life cycle of winds where the patterns that they trace out in the Q diagram. We don't understand what triggers the formation of observable winds. And I think as a consequence, and I'll explain all of this, we don't understand the real world launching mechanisms for these outflows. So there are some big questions that remain to be answered. So let me go through each of these. So we have this life cycle of winds that I like to call it, this pattern of observable absorption features in black hole outbursts. And Gabriele Ponti showed that winds are preferentially detected in softer states, rarely in harder states, and rarely in association with jets. Now there's, Jeroen Homan has a paper from 2016 where he gives some exceptions to that already. And Natalie gave a nice, put a nice word to this in her talk on Tuesday of calling these unexpected winds. These are winds that don't fit into that pattern, but the number of those observations is growing. And so we have to understand that there is not a clear distinction between, it's not a clear state line. There's no sharp line that says you will observe a wind now and you won't observe a wind then. So we need to understand what determines when winds are visible. So I mentioned this paper that came out earlier this year by Pop and Company that is fairly well known at this point that hard spectra, hard ionizing spectra, tend to make thermodynamically unstable winds. So when spectra are hard, you don't necessarily expect to see detectable lines. That can be pretty sensitive to the shape of the spectrum, especially if you extrapolate it to hard X-rays. So you need to be careful with what you're assuming is there and what you're not. But another consequence of this paper is that even if you wouldn't have seen anything in a hard state, in order to get the absorption that we're seeing in softer states, you still require changes in the ionized gas. You don't have a static wind. You have to have some intrinsic variability in the outflow itself in order to explain the phenomena that we're seeing. So we know that it's not just a matter of ionization and not just a matter of thermodynamics, but there's real astrophysics happening too. There's moments when winds are turning on, and we don't have a good sense of what is the thing that's triggering the formation of these winds. Now, theoretically, you can invoke things like a critical luminosity for thermal winds. That's part of the theory, but from an observational sense, that's not something that we've been able to constrain with observations yet. So it's also not just the case that this is relevant for the classic Q diagram outbursts. For example, we saw a couple references earlier this week to this new state of GRS 1915, which was an outburst for 26 years and then suddenly dropped off. And here's a zoom in on the bottom panel of the nicer observations of GRS 1915. And it's entered this obscured state. And there's been a bunch of work done on this over the last year or two that suggests that the drop in flux here is due to the appearance of a Compton thick obscuration and very possibly a Compton thick wind. And if you want to see some nicer spectra that demonstrate that, this is from my paper from last year, where when the source flares, you can really see the Compton thick obscuration that's eating away the soft X-ray photons here, and also you get a big nice iron edge out of it. So we have really nice constraints on this obscuration. But if this is a Compton thick wind, I think it's a fair question of why all of a sudden a long-lived Compton thick outflow would appear after 26 years in outburst when there's nothing that appears to have triggered this. It's completely baffling why something like this would happen just spontaneously. You know, if you had seen a big rise in the luminosity and then it went up and then this wind appeared, that would make sense. But this, I think, fundamentally to me doesn't make sense. So I'm in the dark on that. But then that's just not GRS 1915. We're now seeing a growing number of observations of winds that really look like they belong to Compton thick outflows. These observations that have big long line lists, and their spectra are not the classic disk plus power law kind of continuum. They look more like cold Compton scattering with high optical depth. There's something that we're seeing now in a few different cases in a few different states and different systems that Compton thick outflows from stellar mass black holes, and there are similar examples for V404 Sig by Saramata and others. That this is not a completely unusual phenomenon. We're starting to see this more and more often. So I think we need to be thinking about what can trigger those kind of outflow modes and accretion modes. A consequence of this is that that we don't, and I'll explain why this is a kind of a corollary, but I think we don't understand the launch mechanisms all that well. So in principle, the launch mechanisms that I've mentioned, radiation pressure and thermal driving and magnetohydrodynamics, can be distinguished by the location in the accretion disk and in ionization. So we have this kind of map of systems that we've come up with over the last 20 years or so, where depending on the distance from the black hole and how ionized the gas is, you can have different mechanisms operating. In order to put any observed wind on this diagram, you need to know how ionized the gas is, you need to know the luminosity, and you need to know the density in order to find that this particular wind is consistent with a thermally driven wind or not consistent, or could be driven by radiation pressure or vice versa. So, if you find that a wind is in the outer accretion disk and it's moderately or fairly highly ionized, you could say, well, that could be a thermally driven wind. If it's, generally say if it's closer to the black hole, you would tend to say that, and it's hot, you would tend to say that would be a magnetically driven wind, or if it's cold gas, it could be driven by radiation pressure. Now, part of the to get subtle about it is all of these mechanisms should be operating at some point. The accretion disk is a magnetic flow, and so to some extent there should be a magnetic wind, but which of those dominates, which of those processes dominates in any given system at any given time, is a real question. So that's kind of
about 5 minutes.
Thanks, Mike. So what does this have to do with Compton thick winds? Well, the cases where we can measure the density of the gas are very few and far between. But in some cases, like in JRJ 1655, there are absorption lines, there are atomic lines that are sensitive to the density. Now these are at 11 to 12 angstrom, so they're 1 keV and below, depending on which element you want to look at these critical density sensitive lines for. If you can measure these lines, you can figure out their ratio and estimate the density in the gas. Because they're in soft X-rays, they're only useful for sources that are not directly in the galactic plane. But when you take that density and you use it to calculate a radius from the ionization parameter, you've got your ionization parameter and your luminosity, and you finally find your density, you turn that into a radius, you have to understand the emission geometry in order to turn that ionization parameter into a distance from the black hole. What you're really doing here is looking at the flux per electrons per cubic centimeter. And so the flux, if your emission geometry is not a point source, but a massive Compton thick outflow, then you risk drawing the wrong conclusions from your ionization parameter. So to the extent we can only understand the driving mechanism to the extent that we understand the outflow structure. So my example of this is what was interpreted as an MHD wind in 1655 is actually Compton thick, and that makes it much harder to figure out what the launch mechanism actually was. So what to do about it? There's a couple things that we can do. Natalie mentioned this, and Teo Munoz-Darris has been doing a lot of work on this in the last few years. Optical spectra, for example, optical and infrared spectra do show winds in black hole hard states. And so here's a P Cygni profile in a hard state that Teo Munoz-Darris observed in V404 SIG. And what's interesting about this is that optical spectra show us very, very different ionization states in the gas than the X-ray spectra. So and that's in hard states, we're clearly missing something about the physics of winds, and the fact that we have such a huge range in ionization in this gas. We're not taking advantage of that. That's information that we need to make better use of. And I say that to the X-ray community and really myself, we need joint spectroscopy. We need to be doing these campaigns jointly with X-ray and infrared or optical in order to be able to really study these, to understand these winds in detail. So that's one thing that I think we should be doing in the future. The next thing we can do is look towards future missions that are coming up, like CRISM, Athena, and maybe farther down the line, Lynx. If you look at, if you simulate what an accretion disk wind might look like in a 30 kilosecond observation with Chandra, come back here, you might see a marginal detection of an absorption line, depending on the ionization and the column density and so on. Those detections that are marginal in data now are going to be extremely significant with next generation X-ray telescopes. This is 30 kiloseconds with CRISM. This is 10 kiloseconds with Athena. So as we launch our next generation facilities, we're going to be much more sensitive to the appearance of absorption lines. And so as we target those states where we want to find absorption, we're going to be much more sensitive to them. So even if they're there now, we just can't find them with the quality of data that we have. We can look forward to that. But I want to make a caveat here, because this is a spectrum with links from the cat gratings and the microcalorimeter that I simulated to look just like JRJ 1655. This is 100 kiloseconds of data. I don't think we're ready for spectra like these as a community. if you look at the statistics, the usage statistics for Chandra transmission gratings and XMM gratings, I think the community, the X-ray binary community in particular, is not really preparing to analyze spectra that look like this. And so I think we need to, I'll say this again, but we need to get ready for complex line spectroscopy, and that means better usage of the HETG, trying to focus more on developing tools and expertise in high resolution spectroscopy, so that we can actually, if we wait until those next generation facilities launch, I think it's going to be too late. So let me wrap up and say that the last 20 years have produced a lot of really exciting revelations about disk winds. I think there are a lot of open questions still to be answered. I think we should be focusing on trying to target these states at fairly high cadence to catch the turn on moment that and these baby winds is what we're looking for. I also want to finish by saying happy postdoc appreciation week. I'm very happy to have both the current and former postdoc Greg Marcel and Federico Vincentelli here, and it's a pleasure to work with young scientists like these who are doing such great work and are so much fun to work with. So I'll stop there and take any questions.
Okay, thanks a lot, Joey, for ending bang on time. Please post any questions you have in the Slack channel. And I don't see any yet, so we have some coming in from Hermanth. A quick question. Are atomic absorption edges the only observable indication of disk wind? Is there any other way to confirm it?
So you can see, in principle, a few different features. Sorry? Okay, can you somebody turn the volume on? Okay, so yeah, you can see absorption lines, you can see absorption edges. In principle, depending on the inclination of the system, you might also expect to see emission lines or some scattered light. But in terms of observable features, I think those are basically it. Yeah.
There is a question in the room.
Hi. At the beginning of your talk, you had this formula for m dot, which contained omega over 4 pi, and m dot wind was comparable to m dot accretion, at least from my reading, unless I'm mistaken, if omega is above 4 pi. But you also said that winds are confined to the equatorial place, and also they are detected only in high inclination systems. So I thought that omega is much less than 4 pi.
Yeah, and that's fair. And this is this estimate is a bit hand wavy. The point is that I guess I would say two things. One is that whether whether you can see these winds in the opening angle is probably at least 30 degrees. But whether it's within a factor of 2 of the accretion rate or 3, the mass loss rates are significant here. The other thing is that the ionization of the wind may be a function of angle off the disk, and so it might be easier to observe some of that gas along lines of sight that are closer to the equatorial plane.
Okay, we have a question from Poshak. Poshak, maybe you can just jump in and ask it.
Thank you. Thanks for the nice review. It's along the lines of what was asked before. You mentioned emission and scattering. In AGN, we typically see very strong iron K alpha in Compton thick AGN emission lines. Wouldn't you expect to see that here as well, given the opening angles that you mentioned and that the varying ionization states?
Yeah, and so I mean the one case that where we're one of the cases where we're really confident that there's Compton thick obscuration, which is this new obscured state of JRS 1915. If you look at the spectra at low luminosity, when you're really just looking at the scattered emission, or what we think is the scattered emission, let me pull it up here. you do see some emission lines, both cold and ionized. So here in the low state, when you're not flaring, you have iron K alpha, and you also have hydrogen and helium like iron emission. So so in that case, I think that is observed in some cases.
Do we have a quick question from the floor?
Yeah. Yeah. Yes, please.
Hi, here is Agata Różańska. I have a comment on those stability curves you were presented, because the photoionization is much more complicated that you shown. I mean, it depends on density really, and it was shown in many papers that it depends above certain value of density. So if density becomes comparable to the disk atmosphere, it really depends, and depends on heavy elements abundance. And of course, on the shape of spectral energy distribution. And I think we should talk, Bob, because in your paper, you are saying, this paper you have cited in your review, that it does not depend, which is completely something to discuss really, and to make it clear.
If I can answer, indeed, we can discuss. There are some dependency, of course, but apparently it's not strongly dependent on the, for example, on the abundance, but of course on the density, the effect can be important, not at this temperature anyway, but
probably for your spectrum, for your special spectrum is not maybe so strong dependent, but you have to have hard spectrum as it is in.
Yeah, and I guess what I would say briefly, I know we're about to wrap up, but the lines that we're looking at here in these spectra are primarily not sensitive to density. So your ionization balance is certainly sensitive to density, especially once you get to these high densities that Agata mentioned. But it's not clear that we're close to those densities in most cases.
Okay, let's thank Joey again.
Thanks, everyone.
And